Hello, my name is John Singleton, and my talk today is called Survival of Neutral Fermions into the High Magnetic Field Kondo-metal State of Ytterbium dodecaboride. This is a collaboration between Lou Lee's group at the University of Michigan, Kyoto University, the National High Magnetic Field Laboratory's Pulse Field Facility at Los Alamos, and Ibaraki University. And I'd like to single out Zijie Jiang, who contribute a lot to the experiments and to the theory and the analysis of today's talk. So what I'll talk about is a pulsed magnetic field study above the Kondo insulator to Kondo metal transition at 45 Tesla in ytterbium dodecaboride. And what we see are quantum oscillations in the high field Kondo metal state using fields of up to 75 Tesla. And these quantum oscillations, we believe, are due to the same quasi-particles that give quantum oscillations in the insulating state. So as we've heard before, ytterbium dodecaboride is a Kondo insulator. The band gap opens up at low temperatures due to hybridization of localized F electrons with conduction electrons. This is a variant of the Kondo effect. Consequently, as we decrease the temperature, the resistance increases into a very insulating state. And then there's this unusual saturation at temperatures below about 2 Kelvin. In this insulating state, we do get quantum oscillations. We get them in the resistivity and also in the magnetization. The latter is a very important observation because the magnetization is a thermodynamic function of state, and therefore it's directly relatable to the density of states of whatever it is that's causing those oscillations. The amplitude of these oscillations fits the Lifshitz-Kossievich formula as a function of temperature, and this is a surefire identification of fermions. These oscillations must be due to an oscillatory fermion density of states. But of course, this thing is an insulator. So these, we suspect, must be neutral fermions of some sort. The oscillations allow us to deduce the size of a neutral fermion Fermi surface and its temperature dependence of the oscillations give us the effective mass, and they agree with the low temperature fermionic contribution to the heat capacity and thermal conductivity of ytterbium dodecaboride, which implies that all of this stuff is a bulk and not a surface effect. So in today's study, I'll describe what happens when we go above 45 Tesla. It's been known for a while that the resistance of ytterbium dodecaboride collapses to a very low value at a field of about 45 Tesla. So what was known about this? So the conductivity is very high. It looks like some sort of a metallic state. Pulse field heat capacity measurements carried out by Terashima show heavy fermions. There's a fermionic contribution which is attributable to electrons with very high effective masses of about 100. And this is at 60 Tesla. So what we're getting is a transition from a Kondo insulator to a heavy fermion like Kondo metal state at 45 Tesla. So what happens to the neutral fermions? Well, to see this, we use the PDO or proximity detector oscillator technique. This involves putting a coil of 50 gauge wire around a sample. And what happens is that this coil is part of an LC circuit driven by the oscillator. As we change the magnetic field, changes in resistivity change the skin depth of the sample, which shifts the coil inductance. And that gives us a change in the resonant frequency of the PDO circuit. So we measure the frequency versus the magnetic field, and this technique is sensitive to skin depth or conductivity, and to a lesser extent to the magnetic susceptibility. So in the low field Kondo insulator state, and we've got magnetic field down here and frequency up here, we have a large resistivity and a large skin depth, and therefore we get complete penetration of the megahertz oscillatory fields. This featureless data, just a slight background due to the magnetoresistance of the copper coils. As we cross into the high field Kondo metal state though, the resistivity is small, we get a small skin depth, and therefore we get the PDO sensitive to things like quantum oscillations occurring in the conductivity and the magnetoresistance. We also get a signature of the phase boundary here. Notice there are data for several different angles of the magnetic field with respect to the crystal. This setup is on a rotation stage. So once we subtract the background magnetoresistance, we can see these oscillations very clearly. These are for several different angles here. The first thing we notice is that the strong spin splitting of the oscillations. You can see they occur in pairs here. And this is in contrast to the Kondo insulator state where no spin splitting is seen. We can then allocate an index to each oscillation and plot them versus 1 over magnetic field. And we find that rather than lying on a straight line, they lie on a curve. They're not periodic in 1 over B. And this is unlike, again, the Kondo-insulator state. The oscillations behave very conventionally and lie on a straight line as a function of 1 over magnetic field. So if we look more closely at this non-linear dependence on the 1 over magnetic field, we find that it's actually given at each angle by a relationship like this. We've got an integer plus a phase factor equals a frequency in Tesla, and instead of being over the magnetic field, it's over the magnetic field minus an offset. And this offset is the same, 41.6 Tesla, for all of the angles, but the frequency varies with the angle theta. The second thing to notice is that the oscillation amplitudes fit the temperature-dependent part of the Lifshitz-Kasiewicz formula. You can see it over here. As before, the Lifshitz-Kasiewicz formula is essentially a derivative of the Fermi-Dirac distribution function, and therefore we can say that whatever these quasiparticles are, they really look like fermions. So let's now examine this dependence on field a little bit further. We've already heard that the Kondo-metal state oscillations occur at fields given by an integer plus a phase factor equals a frequency over an offset field. Well, what we can do is turn this around and express this instead in terms of a field-dependent quantum oscillation frequency, which is this. Now, if you do the derivation, the Onsager proportionality between the extremal orbit area of the Fermi surface and the frequency still holds, even if they're both functions of the magnetic field. So what we're actually seeing here is a change in the extremal area of the Fermi surface as a function of magnetic field, given by this proportionality down here. Anyway, we have this relationship, and that means that we can follow the frequency back towards the phase boundary. So here we see this relationship. The red solid line is where we can actually see and fit it to oscillations very precisely. The dotted line is the extrapolation. The gray region here is the spread of field over the phase boundary. And you can see that this extrapolation goes back very, very closely to the frequency of oscillations we see in the Kondo-insulator phase. This very strongly suggests we have the same Fermi surface responsible for the quantum oscillations in both the Kondo-insulator and the Kondo-metal states. And this seems to be true for all of the angles that we apply the magnetic field. I'm going to note briefly here that the effective mass also changes with field, and that could be coming up in the discussion that we have later on. So let's just recap. The back extrapolation of the quantum oscillation frequency in the Kondo-metal state gives the quantum oscillation frequency in the Kondo-insulator state pretty precisely at the phase boundary. So this very strongly looks as though the Fermi surface detected in the Kondo-metal state is the same as that in the Kondo-insulator state. We've attributed the Kondo-insulator state Fermi surface to neutral fermions. We can ask, are they still neutral in the Kondo-metal state, or have they acquired some sort of charge? And we can also ask, why is the Fermi surface depopulating as the field decreases? So what we're going to do is to try to answer these questions by measuring the conductivity in the Kondo-metal state properly. Before we do that, let's just look at the expectations. If the magnetoresistance in the high field state is due to the same piece of Fermi surface that causes the quantum oscillations. Now, we already know that this has a frequency which is very field dependent. We can convert that into a number density of quasiparticles, which is field dependent. We also know, I mentioned it briefly, that the effective mass is field dependent. So if we substitute both of these things into a Drude-like formula, we find a resistivity that will be very dependent on the magnetic field in the Kondo-metal phase. So if we see a very strong magnetoresistance, we can attribute it to these quasiparticles that are causing the quantum oscillations. If we don't, then they're only a secondary feature of what's going on. To make a precise measurement of the resistivity using pulse fields in the low resistivity Kondo-metal phase, what we need to do is to apply a very high current. We also need to apply a high gain to our amplifiers. But of course, if we used a high current in the Kondo-insulator phase, that would heat the sample and saturate our electronics. So what we do is we gate the current that we apply to the sample. This is the current on the right-hand index. This is the field on the left index, so that it's only applied when the field is above 47 Tesla. This avoids the heating and overloading issue. And so the typical magnetoroesistances that we see are actually very, very flat over a range between about 48 Tesla and 70 Tesla. There's not much field dependence at all. So this means that the resistivity that we see is not due to the same quasi-particles that gave us the quantum oscillations. It's due to something else. And then maybe at the highest fields between 70 and 75 Tesla, the resistance starts to go down, and this is perhaps some other phase coming in, and we've not had the magnetic field to examine what that might be yet. So here's a summary of the temperature-dependent resistivity in the high-field Kondo-metal state using this pulse current method. There's very little magnetoresistance, so we're just going to plot the 55 Tesla values of the resistance as a function of temperature. This is about the middle of the flat magnetoresistance-free region. And as we've said already, the quasi-particles that give the quantum oscillations play little or no part in the conductivity, because otherwise we'd expect a big magnetoresistance. Also, because there's very little magnetoresistance, there's very little disorder. So the conductivity in the high field state is dominated by a large Fermi surface of heavy electrons. This is the thing that shows up in the 60 Tesla pulse field heat capacity data. So if we look separately at the low temperature behavior and plot it as a function of T squared, we see that the resistivity values lie very nicely on this straight line. So we have a T squared behavior that's expected for heavy electrons. But as the temperature grows, we get a transition to a linear behavior, which is plotted up here, a resistance which is characteristic of strange metals, seen in things like pnictides and high TC cuprates in their normal state. So what's actually going on in this Kondo-metal state? We know from the heat capacity measurements, the Kondo-metal has a large Fermi surface of charge-carrying electrons. These things appear to dominate the electrical transport and the thermal properties. The electrical transport because we have almost no magnetoresistance. However, their masses are very heavy. We know that from the thermal properties in the pulse field measurements, and we get no quantum oscillations due to this Fermi surface. Instead, the quantum oscillations seem to be still due to the neutral fermions, because we can extrapolate back their frequency to the phase boundary, but this frequency is now field dependent. So what we propose is in the high field Kondo-metal state, the additional fermion reservoir, the Kondo-metal Fermi surface, that's not present in the low field Kondo-insulated state, it exists and the neutral fermions start to depopulate into it. This gives us our field dependent quantum oscillation frequency. There's support for this sort of two-carrier picture from Patel-McGreevy-Sachdeva theory, which is applied to strange metals. And what that says is if we have a presence of two quasi-particle reservoirs, one of which is electrically inactive and the other which has a conventional Fermi surface between which you can get scattering, that leads quite naturally to a T-linear resistivity. And we do see this T-linear resistivity. So that tends to support this sort of coexistence of two Fermi sections, one which can't carry charge and the other which can. So why are we seeing quantum oscillations? Well, let's start with the insulating state. How can you get quantum oscillations in the resistivity due to neutral fermions? Well, even in conventional metals, quantum oscillations in resistivity are hard to model. If we read Schoenberg's book, what he does is he uses an approximation due to Pippard, which proposes that the rate of quasi-particle scattering is proportional to the density of states available. This is just a Fermi golden rule argument. Of course, our situation is a little bit different. In the Kondo-insulated state of ytterbium dodecaboride, the resistivity is due to electrons thermally excited across the gap, plus poorly characterized states that give us saturation at low temperature. So this is this sort of dilute electron gas I've plotted here as a density of states. The fermions in the Kondo-insulator state scatter back and forth between the charge neutral Landau levels and the more normal electron states. But the Landau levels, of course, oscillate as we change the magnetic field. Their density of states is oscillatory. So this is more complicated than Pippard's concept. We're dealing with scattering between two bands, but the amount of scattering is given by the joint density of states. And so we get an oscillation of the resistivity because the density of states of the neutral quasi-particles is oscillating as a function of magnetic field. So unlike conventional metals, the density of electrons that are actually doing the charge carrying is temperature dependence. So Shubnikov-de-Haas oscillations in the Kondo-insulator state will follow a different temperature dependence than de Haas-van Alphen oscillations in magnetization do. And they do indeed do this. So turning now to the high field metallic Kondo-metal state, the quantum oscillations in resistivity, they're still due to these neutral fermions. So what's going on here? So we have a neutral fermion gas cohabiting with a heavy fermion metal. The evidence for the heavy fermion metal is the heat capacity at 60 Tesla, the conductivity. These are ordinary but heavy charged electrons. So what's happening is now we have a reservoir of heavy electrons, and you're getting scattering between the neutral fermion Landau density of states and the heavy fermion density of states. So the rate at which this scattering occurs will be proportional to the joint fermion density of states. And because the neutral quasi-particle density of states oscillates with the magnetic field, so will the conductivity, which is dominated by the heavy electrons, and hence the skin depth. So the quantum oscillations are due to this heavy fermion density of states reacting, scattering with the neutral fermion density of states. We don't get quantum oscillations from it because the effective masses are actually about 100, and our relatively high temperatures used for the measurements, 0.4 Kelvin, will suppress any oscillations used to those. So the resistivity oscillations, seen as skin depth oscillations, are due to this exchange of quasi-particles that's going on. So in summary, the high thermal conductivity, the high electrical resistivity, and the quantum oscillations in the low field state of ytterbium dodecaboride imply fermions that are electrically neutral. In the low field state, these neutral fermions cohabit with a Kondo insulator. As we cross the boundary into the high field state, the Kondo insulator changes to a Kondo-metal. The Kondo-metal has a large Fermi surface of charge-carrying electrons that dominate the electrical transport and thermal properties. However, their masses are very heavy, and so we don't get quantum oscillations due to this Fermi surface. The quantum oscillations instead are due to the persistence of neutral fermions, and the evidence for this is given by things like the T-linear resistivity. And in the high field phase, the additional fermion reservoir, the Kondo-metal Fermi surface, exists, and the neutral fermions start to depopulate. We get a field-dependent quantum oscillation frequency. And because of scattering between these, we can see these oscillations due to the neutral fermions in the conductivity of this high field Kondo-metal state. Now, I have to say that both of these phases, the low field state, the Kondo insulator, where you get it cohabiting with these neutral fermions, and this high field state where we get a Kondo-metal, a heavy fermion metal cohabiting with these neutral fermions, they're a new state of matter. Anyway, more information on all of this is given in this preprint, which will be out in Nature Physics shortly. If you want one of these, please don't hesitate to email me at jsingle@lanel.gov.